All right, Unit 12 looks at some properties of logs and how we can use these to solve some different kinds of equations. So there are lots of properties you talked about, but there are three main ones we use, where we can add two logs, we can subtract two logs, and then we can have a power or a number out front of a log. So if you have two logs added together with the same base, this is all predicated on being the same. These are just base 10 because there's nothing there, but they have to have little, they could have both have little 2's here or something like that, whatever it would be. So when you add them, you can make them one log of a product. When you subtract them, you can make them one log of a quotient. And again, you want to make sure that the second one comes on the bottom. And if you have a number out front, you can actually bring this up as an exponent of the log. So this works both ways. I could start on this side and go this side, or I could start with any of these and go backwards. Most of the time in this class, we're going to be combining logs, so we'll start on the left and try to make it look like something on the right. But in more advanced math, we actually try to make them simpler and smaller things, so that's something you might do in the future. So there are two types of equations we're going to solve. We're going to solve exponential, and we're going to solve logarithmic. Now, the best way to solve an exponential, there are basically three ways. The best way is to get the bases to match, and we've seen that before. If the bases match, then we can just set the exponents equal. So that would be our best case scenario. You have the same base, you can set the exponents equal, go about your business. The second part is we want to isolate the exponential and then switch to log. This works really well if you have only one variable, like if you only have one x in one of the terms. If you have multiple terms with x's, this does not work so well. And as you saw in your notes, the Edpuzzle notes, the last way is we can take the log of both sides. Now this one is not the prettiest way to go, but it does work. I don't believe there are any of those on today's worksheet of the day, but there certainly are some in your ALEX that you will probably come across. So when I look at these three kind of techniques we can use, and I look at a problem, I'm first going to see if I can get the bases to match. So I see I have a 3 to x plus 1, and I have a 1 to the 81st. So I look at the 3, and I start thinking about different powers of it. So 3 to the first is 3. 3 to the second is 9. And I'm trying to see if any power will give me 1/81st. Now if I see 3 to the fourth gives me 81. 3 times 3 times 3 times 3. But I have 1/81, but that's okay. Because remember, if it's a fraction, we can always change this. This could be 3 to the 2x plus 1 equals 3 to the negative 4. So if you see something that is the denominator, you can just add that negative, and then you have your equation you can solve. So now these bases are the same. I can just set these exponents equal. 2x plus 1 equals negative 4. And doing some algebra, we can make this x equal negative 5/2. All right, let's look at this next one. So if I try the same technique, if I try to take 6 to some power, 6 to the first is 6, 6 to the second is 36, I'm not going to get 7. That's obviously pretty evident in this one. So what I'm going to try to do is, since there's only one x, I only see the one x here, I'm going to switch to log. Now I will forewarn you, there are cases where maybe I have a 3 out here. Well, just remember, if there's a 3 out there, I can certainly divide both sides by 3 first, or if there's a number added to this exponential expression. But you want to make sure you get your something to a power by itself, which in this case it already is. Well, if I have that, I can just switch to log. Recall exponential form, which is this, can be turned to log form, which is this, so it's just a rearrangement. So it's log base 6 because the bases are the same, but whatever was by itself is now in the log, so that's 7 equals x plus 3. Now log base 6 of 7 is some number. I don't know what it is, but we could put it in the calculator. So that's some number. So to get x by itself, we'll just subtract 3. So x is going to equal log base 6 of 7 minus 3. And recall, if you're using a traditional graphing calculator or scientific calculator, the change of base formula is how we find this value. So we do log of 7 divided by log of 6, and then minus 3, and that would give us our approximate x value. This is our exact, and then if I want to put it in the calculator, that's what I type in to get our approximation. And obviously, if you're doing ALEKS or something, make sure that you check what it rounds to, because it will mark off if you round it incorrectly. All right, our last kind of equations we're going to see are log equations. And log equations, there are typically two types. There are ones where everything has a log. So everything has a log, so all the terms have a log, like this one. And then the second type is when only some of the terms have a log. So one property that we really didn't talk about that's pretty important, if I have log of the same base on both sides, log of A equals log of B, then that just means A equals B. So if you have a log of two different things, that means those things have to be the same. So that will help us when all terms have a log, similar to this problem. 1/3 log base 7 x plus 1 equals log base 7 of 4. Now before I go anywhere, you notice there was no number out front of this log, so I have to get rid of that 1/3. But one of our properties says if I have a number out front, I can just bring it to the top. So I can rewrite this as log base 7 x plus 1 to the 1/3 equals log base 7 of 4. So now because there's only two terms and they both have a log, that means the stuff inside has to be the same, so we can quasi-cancel. So x plus 1 to the 1/3 equals 4. And so now I'm just left to solve this one. So I'll go ahead and cube both sides, because 1/3 is like a cube root, so I could have wrote it like cube root and cubing it. So I could write it like that. So that's going to give me x plus 1 equals 4 to the 3rd, which is 64. And then subtracting 1 is going to be 63. Now this is probably my solution, but here's the one thing about logs. We have to make sure we plug it in for x, and the one big thing we have to make sure is it can't make it negative. So 63 plus 1 can't be negative. It of course isn't negative, but if it was negative, we'd have to exclude it as a solution, and we'll see that in the next problem. So in this one, our only solution is 63. Now this one you see is a little bit different, and namely because we have something that has a log, this has a log, but this has no log. It's just the number 1. So in this case, we're going to have to use our switching forms. Now I do have these two logs on this side, and that's good. And so what we'll generally do if we have two logs added, remember we had that property at the beginning that says if you have two logs added, you can write it as one log of a product. So I can make it log of x minus 9 equals 1. So there's not a good way to get rid of log here, so I'm going to have to switch to exponential form. Now remember, in this one it just has log, which means it's going to be base 10. ln is base e, log is base 10, unless there's a number down there. So if I switch forms, I'm going to get 10 to the first equals x squared minus 9x, and that's simply just by distributing. So I'm just switching forms. Base to what was by itself equals the stuff in the log. Again, that goes back to the previous thing where we had that switching. So now we get a quadratic, and this is a super familiar problem. I would guarantee you'll see this on your test, on your quiz, on your final exam. They love to see these kind of problems in ALEKS. So we get 0 equals x squared minus 9x minus 10. So this factors is x minus 10, x plus 1. So x is going to equal 10 or negative 1. But I'm going to claim that negative 1 is no good. Because if I plug in negative 1 for x here, negative 1 minus 9 is negative, and logs can't be negative. In fact, if I put negative 1 here, it's also negative. It only has to violate it for one. This one violates it for both. 10 is fine because 10 minus 9 is 1, and 10 is 10, so 10 is the only valid solution. Really important to make sure in a log equation, if you get a negative value when plugging it in, you have to exclude it. So just a couple examples on Unit 12 and the worksheet of the day. So if you have questions, obviously, please contact me, let me know.